Good morning, everyone. Thank you for joining today's tNavigator webinar. My name is Joanne from RFD's Aberdeen office, and today we have quite a global team of presenters. So we've got Maria from our London office, Tibor from Budapest, and Zach is joining all the way from Perth, Australia. This is the second part in our current webinar series. If you missed our webinar on Tuesday on integrated asset modelling, you can find it on the RFD YouTube channel, and we'll upload today's thereafter as well. And today's session, we will be demonstrating how you can use a range of hydraulic fracture modelling options in tNavigator to understand uncertainties and address key challenges.
Yeah, so...
Oh, sorry, Tibor, 1 second. So everyone in the webinar has been automatically muted. So if you do have any questions, just pop them into the chat box and we will answer as many as we can at the end. And the session's been recorded. As I mentioned, we'll upload it to our YouTube after, and you have our email address there if you have got any further questions for us. So I think I'm going to hand over to Maria first, just to present the first part, and then we'll move on. Thanks.
Thank you so much, Joanne, and thank you everyone for joining us today to discuss tNavigators and advancements in geomechanics for optimized hydraulic fracturing modeling. Throughout this session, we will explore the main hydraulic modeling challenges that need to be addressed to fully realize its implementation in any producing asset. We will explore the benefits of integrating reservoir characterization modeling directly with both observed and dynamic changes that occur during the hydraulic fracturing and after, when the fracture is already implemented in the well. This comprehensive approach ensures that a more accurate representation and understanding on how fracturing impacts the reservoir is going to be seen and evaluated at different development stages. Key to the entire process is the integration with geomechanics to account for mechanical changes in the rock and environmental effects, aiming for more optimal modeling strategies for field development. To conclude, we will demonstrate the power of enhancing fracture parameters to achieve a maximized production from any of the wells that have been selected to add a hydraulic fracturing, and to conduct a risk assessment at all relevant levels of the modeling. Tibor Tooth here in this presentation is our technical advisor, and he will begin by discussing geomechanics modeling.
Welcome everyone. So what happens when reservoir depletes and it's naturally changing the stress? So when pore pressure drops, the net stress increasing on the rock. Now it's not only increasing induced by depletion, but also we have the tectonic components. We have a directionality to the stress itself. We have a maximum minimum components that all can be incorporated into the model. It's quite important to incorporate these changes of the rock, because at certain net stress, the rock will eventually fail. So when the rock fails, then you would have fractures, and some of these fractures are convective. So simply, we have a capable software modeling the full field geomechanical features is fully coupled at all time with the simulator itself. So we have two elements. We have the finite element calculation using the grid to split the 6 tetrahedron, and then we do have the finite difference model all in one. So the connection between them are continuous, that every single time step we calculate stress and we calculate the pore pressure and saturation changes as well. On the next slide, we see the type of approach. Yes. So these are the main components of our modeling. We have fully coupled module. We have elasticity and plasticity terms there. We have the fluid filtration, and we have the multi-phase flow criteria in the first line. You have the conservation of rock mass as well, and you have a geomechanic equation following the name equation in linear elastic media with displacement factors. And of course, we have the conservation of mass as a fluid inside the porous media. We have different boundary conditions. We have Dirichlet boundary condition, Neumann boundary conditions. We can use stress and strain boundary conditions to accommodate the tectonic components of our reservoir. We have a couple of failure criteria to count the most obvious failures. We have the Moore-Coulomb criteria. Can we move to the next slide, please? Then we have a bit more details on the failure itself. So obviously, for the failure of the frac, this presentation is focusing on the hydraulic fracturing. So the Barton-Bendis criteria is used to initiate a frac where the tensile strength is so high, the shear strength, the ultimate shear strength used by UCS correlation will create shear failure, so the fracture will open. At that point, we have an open fracture that can be calibrated through a breakdown analysis from frac simulator, or we can use frac simulator model stress in tNavigator by importing. We also have a Moore-Coulomb failure criterion on all the other grid blocks, and also we can mix it with a different failure mechanism. For example, we can add a Griffith criterion on the fractures and faults. You can define different regions for different failures and different objects as well. In the next slide, you see a simplified method on how the stress works. We have obviously model grid deformation. We model displacement, strain, and eventually a subsidence of the top reservoir. The direction of the stress is calculated simultaneously. You can visualize it by vectors. You can use streamlines to demonstrate as the fracture becomes active in the model, you change the flow pattern. So from radial flow, you have a bilinear flow. So it's quite easy to have an overview and a QC visually as well by well or region by region as you wish. Now, in the second part, I'm handing over to Zach, and he's going to show you some of the modeling aspects of the hydraulic fracture itself.
Thanks, Tibor. Thanks for the introduction to Geomechanics, and let me explain a bit on the methods that we have for hydraulic fracturing modeling in tNavigator. There are basically two main ways of modeling fractures in tNav, which are the virtual connections and the LGRs, local grid refinement. So for virtual connections, you specify a fracture geometry, and from that fracture geometry, tNav builds the connections to the model grid blocks this fracture communicates with. So you're basically integrating the fracture directly with the well. So in a sense, the fracture becomes a part of your well when you're modeling it via the virtual connections. Second option is a more advanced one, is a LGR or local grid refinement, and you can have uniform, logarithmic, or unstructured gridding within LGRs. This basically implies that you can explicitly define any complex geometry of your fracture that you might have. Another option is to load the point set of your fracture into tNav model designer, and from that, tNav will build the unstructured grid around this complex geometry. This option is going to be very useful if you want to, for instance, import the data from some external software. For this, we support different formats such as gslib or CSV. And the final option is to actually utilize the fracture simulator model that we have. So the simulator model itself has the fully coupled 3D geomechanical model embedded to it. So you can actually simulate the fracture propagation in 3D within your rock based on the input data that you have to feed to the simulator. And this data would include the geomechanical properties, fluid rheology, injection regime, rock failure criteria, and some other. Now I'm going to show you some of the example of how hydraulic fractures can be modeled using the virtual connection and LGRs using the fracture tables. Yeah, so here we have a fracture table. We pick the wells the fractures are going to be assigned to, and specify some other parameters, such as the number of fractures, for instance, at the particular interval. We can also adjust the fracture half length, as you can see, and we can visualize what's going on in a 3D viewer. So this is how the fractures are placed within the hydrodynamic model itself. This also can be visualized in a 3D and seen. And we have to also have to enable the fracture table within the development strategy, so the fractures are integrated into the dynamic simulation. So here you can see the pressure distribution around the production wells, where the fractures modeled with virtual connections. As you can see, the grid itself is not affected, and the numerical mesh stays unchanged. This is not the case for LGRs, which I'm going to show in a second. So for LGRs, we are using exactly the same fractures, but as you can see, the mesh is much finer within the fracture itself, and there is some logarithmic mesh refinement within the near fracture zone or stimulated rock volume. So at the end of the day, the results are quite similar here. But we have to bear in mind that this is a simplistic model, and in reality, it's typically not the case. And in practice, the selection between the virtual connections and LGR is dictated by the desired level of details in your simulation. So now I just would like to show some unstructured grids as well, and how they can be handled. Yeah, there you can see how the LGRs are handled by advanced unstructured grids, which basically allows for any geometry and any grid to be incorporated into the dynamic model. Yeah, here we set some of the parameters, including the half length of the fracture, stimulated widths, as well as the effective widths and permeability within the fracture and near fracture zone. You can also see some other parameters that we set here. We can also analyze the cross-section and see the permeability distribution within the fracture and near fracture zone that we set here. We can run and animate the simulation and observe how the pressure changes in time. And you can actually see here how the fractures are non-orthogonal to the main grid, but they're still very well handled by the unstructured gridding that we have in tNavigator. Okay, let me go to the next slide. And here I just would like to summarize that within a tNav we have quite a comprehensive modeling framework to account for hydraulic fractures within the dynamic simulations that we run. This framework can be divided into 4 main subcategories. So the fracture orientation can be specified by a fracture path and fracture plane. The extended geometry of fracture and near fracture zone can be specified in a fracture template. In turn, the fracture stage allows to anchor the fractures to your wells, while fracture arithmetic would allow you to set the properties distribution within the fracture and near fracture zones. I also have to mention here that this process can be automated using the workflows and Python that is embedded in tNavigator. So thank you. This is all from my part, and I'm going to pass it to Maria, who is going to talk a bit more about fracture simulator and some uncertainty quantification within hydraulic fracturing. Thank you.
Thank you, Zach. So now that has explained 3 of the methods to implement hydraulic fractures in tNavigator, I'm going to talk about Fracture Simulator. This is a product that calculates the propagation of the hydraulic fractures in the reservoir by considering rock properties, well injection regime, properties for the injection fluid, and the propant and the interaction between the different fractures to account within the solver settings for the fracture propagation. This is a full implicit method that jointly solves the fluid dynamics equations and the elasticity theory. It is all integrated with Model Designer for the processes just described, but also it could be integrated with Well Designer to have the option of interactively choose fracking intervals and well construction. The workflow to set the hydraulic fractures in simulation in Fracture Simulator starts by adding settings to the rock properties, stress properties, and reservoir conditions. Modeling parameters such as crack criteria, Young modulus, Poisson ratio are specified by the user here, and there are different ways of doing this. The principal stress vector could be come as part of the integration with the geomechanics described by Tibor, that is basically a product of the simulation, or it can be added as a constant value. The reservoir conditions such as pressure, porosity, permeability, fluid viscosity, and compressibility are required to calculate the model for the liquid fluid leak-off. Fracking fluid liquids specifications such as propant and pumping schedules play a critical role in the simulation of the fracture propagation. This is a built-in library in which the fluid and propant properties can be chosen from, or the user can specify their own specifications. It is also possible to specify the PVT properties of the slurry to take into account the influence of the slurry leak-off into the reservoir, considering the shadowing effect, and to employ different models for propant velocity. As a result of the fracture simulation, fracture objects such as fracture paths, templates, arithmetics, and point sets can be created to define the fracture within an existing 3D model. Additionally to the modeling advantages just described, using calculations for fracture simulator in the workflow specified in Model Designer will allow the user to integrate any geological and dynamic properties into the modeling processes as an uncertainties and do any sort of optimization analysis on uncertainty analysis. Fracturing parameters among rock properties and pumping schedule can be set as a variables to optimize the processes of fracking. The different modeling steps, either when using fracture simulator or when using any of the described hydraulic fracturing methods specified with direct inputs of the parameters, can be recorded into an automated workflow for quick updates of the modeling process. Uncertainty variables related to the fracture geometry, geomechanics parameters, PVT of the slurry, or the pumping parameters can be added also to the integrated workflow. The analysis of the results after running the uncertainty study helps to understand the expected production enhancement that results from the different evaluated scenarios. Parameters such as number of fracking stages, fracture conductivity, or expected fracture growth will result in a better understanding of the expected recovery and optimized fracture design. In this example that we are just seeing, it is an uncertainty study using an experimental design algorithm called particle swarm optimization, in which 7 different variables were launched, all related to the hydraulic fracture geometry. The results show the impact of these parameters on the total gas and water production. So by analyzing this data, it can be identified the most appropriate fracture design to maximize the gas total production while maintaining low water total production. It could also be specified what are definitely those sort of parameters that will lead to more water being produced from implementing any sort of fracture geometry into these wells. So by doing this analysis, we don't only specify what is the best solution, but also we can specify what are the limits to not infringe into some results that are not wanted in the whole production. Once this uncertainty study is completed, because it's integrated with the Model Designer, results can be fed back into the workflow that has been implemented to update the model in a simple manner, and then just come up with a final realization that is like the most accurate one. To conclude our presentation, we would like to highlight the relevance of using an integrated hydraulic modeling fracturing approach. First is the possibility of using the geomechanics results as input into the fracture simulator. It allows us to analyze and conserve the cap rock integrity within acceptable ranges under different evaluated scenarios. Second, we have just seen an example in which by running an optimization analysis, the best fracture design can be identified to optimize the well productivity. But additionally to this solution, we offer the option of having calculated parameters accounting for fluid phase changes while coupled with definite elements of the geomechanic modeling. These three advantages described and the geological uncertainty managed within the same workflow provide a critical and unique solution to model further processes like CO2 sequestration. So we just hope that throughout this presentation, we have solved basically the main challenges that will come up with implementing hydraulic fracturing into a system, any sort of producing assets. And we have shown the relevance of having an integration within the different parameters coming from the static modeling all the way to the geomechanics and the direct implementation to critical parameters in the pumping schedule, in the fluid properties, and the changes in the reservoir itself. Thank you so much for your attention.
Thank you, Maria, Tibor, and Zach. So now we can move on to some questions. Just a second. So if you do have any questions, yeah, you can pop them into the chat box and we'll try and answer as many as we can. I've picked out a few that have already come in. So let's just look at the first one. So what fracture growth criteria is used in tNavigator to calculate the propagation of fractures? Do we have a volunteer to answer?
Yeah, I can answer that. So users have the option of selecting their fracture growth criteria between two algorithms. One is the process zone stress, or also known as PZS. In this case, the process zone stress can be specified as a constant or as a property being calculated based on the porosity values. The option of calculating it, taking into account the porosity in the 3D model, is another added value of the integration that we have just described. The other algorithm that we have available is the critical stress intensity factor. In this case, the model 1 stress intensity factor needs to be higher than 1 minus the breakdown criteria tolerance multiplied by the critical stress intensity factor. The frac growth criterion and the crack criterion tolerance are specified by the user in this case if the second option is being selected.
Cool, thank you, Maria. Okay, sorry, there's quite a few questions coming in, so I'll just try and pick a couple. Okay, if the geomechanic grids are tetrahedron, how does it connect with the normal grids from the dynamic simulator?
Yes, you're using the corner point geometry from the finite differences, and all the tetrahedrons are actually split by using exactly the same coordinate system. So you can always identify failure criteria convergence from finite element and finite difference grid because you're using exactly the same coordinate system actually.
Thank you, Tibor. Next question. How do you account for overburden or grids out of main geomodel grid?
Yeah, so obviously if you have the overburden correction and you have the vertical stress calculated using the density, so you have to have a density information on the grid that could be calculated from logs, or you can populate by using the porosity model or co-create by seismic. That's number one. Also, you obviously have a tectonic component. So you have a tectonic component out of the main grid, which is the far field stress. So through the stress boundary condition or strain boundary condition, you can define the tectonic components of the stress. And you observe the corresponding stress changes at the well. So if you have calibration data, like mini frac or extended leak of test for SH mean at the well, you can run a parametric study with orientation and magnitude and a far field stress and observe the match at the well, like in normal modeling steps.
Thank you. Next question, in Fracture Simulator, do you have possibility of dynamic grid / dynamic LGR during fracture growth? Any volunteers to answer?
Yeah, I mean, in the fracture simulator, you have the option of calculating the dynamic growth, if that's the question. Basically, and it is worth saying that when the fracture growth reaches the grid boundary, then there are two options that the user can specify to limit the fracture propagation by the dynamic grid. Well, one is by the dynamic grid, and the other option is to extrapolate the fracture beyond the grid boundaries. And the sort of fracture growth will be different depending on the option that the user has selected, but it's all incorporated within the 3D dynamic grid.
Okay, thank you. I'll just work my way through a few more. We do have a little bit more time, and if there's any that we don't answer, then we can follow up with you after. So, how to simulate the fracture growth / propagation into caprock?
So that's actually, I can take that one. So when you have a caprock, you have the material model from the caprock. So being shale, presumably, or marl, you have, or anhydrite in any case. So because we have a fully implicit geomechanical simulator, we know and we calculate the stress during the run. So if the stress is present and calculated and calibrated correctly for the caprock, then the fracture propagation will not extend into a higher stress zone. So similarly to that, we have a depletion in some of the sand. You will see lower stress due to pore pressure drop. Naturally, the fracture will follow that low net stress area, and the fracture will grow into that zone. So either you have high stress by a higher stressed caprock, or low stress area due to depletion or a geobody, or stress shadow from a nearby well, then that will be correctly accounted and calculated during the run.
Thank you. I think there's a couple of questions that are a bit similar. So, and maybe it's also similar to what you just answered, but can we include thermal stress effects in the hydraulic fracture simulation? And yeah, another question about, yeah, can the fracture model thermal effects / fracturing?
Yeah, so we do have the thermal effect in the simulator as a latest feature in 2024. Actually, it's available.
Yeah, it's available, and it's basically the same platform. The user just needs to specify the inputs from there. It can be also specified as an input from the user, or it can be added as a calculation as well. So it is possible.
Thank you. Let's do one, maybe two more questions. So is / how the thermoelasticity accounted for when injecting fluids colder than the in situ temperature?
We have a thermal option. So we have a full-fledged thermal simulator connected to the Geomechanical, the finite difference, finite element model. So we have the material changes, the Young modulus changes due to thermal effect, and then we have conductivity of the heat in the rock. So we can calculate the cool down and the warm up effect of a cooler or a warmer fluid. You can optimize your heat capacities and thermal energy on just to avoid unwanted cool down effect, or also you have a Joule-Thomson effect. You can account for Joule-Thomson effect and calculate the required heat if you actually want to avoid that. So because of the thermal simulator, it can be coupled with the frac simulator seamlessly, then you can account for these effects.
Thanks. Okay, this seems like a nice question to finish on. Any recommendation what fracture modelling method works best?
We describe 4 different fracture modeling options. It really depends on what the user wants to achieve. There are different objectives for each of them. For example, the one that we would recommend the most if the user have the data available would be to use fracture simulator. To have that, the user will need to have more input data, like for example, related to the rock properties itself, the slurry, the pumping schedule, and so on and so forth. However, if it is just, for example, to specify the production enhancement of several wells, for example, with different stages, perhaps something like virtual connections would be more suitable for their modeling objectives. So all the different strategies or options that we described today had different objectives, different limits, and different solutions.
Thank you. Very nice answer, Maria. Okay, I think we will wrap up there today. There's still a few more questions, but we'll download those after, and I'll actually just leave the window open for a little minute in case anyone's got any further questions once we finish up. Thank you so much for joining this webinar today and for all your great questions. The next webinar is next Tuesday, the 19th at the same time, and that's breaking barriers in geomodeling. So a slightly different topic next week. So thank you so much to Maria, Tibor, and Zach, and we look forward to seeing you next week.
Thank you to the attendees. Goodbye.
Thank you. Thanks.
Bye.